Okay, so welcome everyone to today's One World Mathematical Physics of the IAMP. It is a great pleasure to introduce today's speaker, Camillo De Lellis from the Institute of Advanced Studies in Princeton. And Camillo really needs no introduction. I mean, he's a world expert in the theory of partial differential equations and geometric analysis. So it's a really great pleasure to have him today as a speaker, and today he's going to tell us about anomalous dissipation in the Navier-Stokes equation. Camillo, the floor is yours.
Thank you very much. It's a pleasure to be here, and I apologize for the sleep in what should have been like the September talk, and which I messed up with the times. So without further ado, let me just introduce you to the topic that I want to explore today. So it's going to be about the Navier-Stokes equations, and there's going to be a parameter which I call nu, which is a real number. So this is the viscosity parameter. This is going to be positive for the Navier-Stokes equation, but it will also regard the Euler equations. And this is when the parameter, which I call nu, is going to be equal to 0. And we are always in the incompressible setting. So incompressible fluid dynamics. Okay, so these equations, they describe the motion of an ideal fluid. In the case of the Navier-Stokes equation, you're assuming that the fluid is so in both situations, you're assuming that the fluid is incompressible. But in the case of the Navier-Stokes equations, you're assuming that there is a uniform, like a homogeneous friction for layers of fluids which slide over each other. So the Navier-Stokes equations and Euler equation can be packaged together into these systems. So I'm going to explain what the symbols mean in a couple of seconds, but first let me write down the system, which you probably know very well. And for the purpose of this talk, this is a systems of partial differential equations. I'm always assuming that I'm trying to solve the Cauchy problem, which means that I prescribe the velocity of the fluid at some initial time t equals 0. And I assume I am actually on the periodic torus. So U is a vector field, which depends on time and space, and it's defined on the periodic torus. And at time t at the point x, it tells you the speed of the particle fluid, which is occupying the point x, when the time is equal to t. Okay, and P of xt is a scalar, and this is the hydrodynamic pressure. Okay, as you see, the divergence-free condition is actually telling you that the fluid is incompressible. So the amount of fluid that you find in any given portion of the space is independent of time. The density of the fluid is normalized to be equal to 1. And the first equation, if you actually set nu equals 0, is just Newton's law, so the conservation of momentum for your fluid. So like the first one for the Euler equation is the conservation of momentum, and the second one is conservation of mass. Of course, if there is friction, so if nu is bigger than 0, there is some dissipation in the first law. Okay. So what is this nonlinearity which I've written over here? So this is the advective derivative of your velocity. And so if you're writing it in component, so let's say that I want to write this in the, say, J component. This is just going to be UI di uj. Okay, which, because the fluid is divergence free, if I'm looking at sufficiently smooth solution, I can also rewrite in the following way. And often when I'm just talking about solutions which don't have enough regularity, I'm just assuming that I can multiply the velocity so that the velocity is at least square summable. and the derivative is taken outside of this product, so it's understood in some distributional sense if you want, but I don't want to be too precise on this. Okay, so F is an external force. Okay, S is an external force, which I can assume divergence-free, but essentially I can assume it as divergence-free because without loss of generality, if I decompose F using the Helmholtz decomposition into a divergence-free part and the gradient, I can always absorb the gradient in the pressure over here, right? So just without loss of generality, I'm going to assume it's divergence-free, but I'm not going to actually concern myself too much with this assumption. So during the talk, I will mostly ignore it. But in all the examples that we're going to look, actually, F is divergence-free. Okay, as we said, there is conservation of mass, there is conservation of momentum, but there's also a balance law for the energy, which you find mathematically if you scalar multiply the first equation by U. Okay, so for smooth solution, and in fact, you just need a little bit of smoothness, for instance, for C1 solutions. So for sufficiently regular solutions, okay, you scalar multiply the first equation by U, and you let me just reduce it for a moment so that you can see the equation. So you scalar multiply this equation here by U, and when you multiply this equation by U, you find after a little bit of algebra the following identity. So the time derivative of the density of the kinetic energy has a flux term, which you can rewrite in the following way. Okay, and then as a term which is coming from the dissipation, and the term which is coming from the dissipation can be written in the following way. So there's going to be your parameter nu, and then there is the Laplacian of modulus of U squared divided by 2. Okay, but then there's going to be a minus, and then there's again the parameter nu, and then there is the derivative of your velocity squared. Okay, so that's the local balance law for the kinetic energy. And if you integrate this, you actually find the conservation law for the total kinetic energy. So if I take the time derivative and I integrate this equation in space, so you see, of course, that there is a flux term, this divergence term, which is going to disappear because I'm assuming I am integrating over the periodic torus. If you are, say, in the whole space, or if you are in a domain with boundary, then you have to make suitable assumptions to make that flux term disappear. Another term which disappears, of course, is this one here, which is also a flux, because there's the Laplacian outside. And so what survives is the term which has a sign, which is this term over here. Okay, and this is what you would expect somehow from an honest solution. So the present of a dissipation makes actually the kinetic energy go down in time, right? So if nu is equal to 0, so if you are actually looking at the smooth solution of the Euler equation, then the total energy is actually preserved. So there's no dissipation. And the equation is energy conservative. You also notice another thing. Of course, if nu is bigger than 0, so this gives you an arrow of time for your equation, right? So the energy is dissipating for positive times. But also, as you can easily imagine, if you have certain familiarity with partial differential equations, when nu is positive, the equation has more of a parabolic flavor, and it's going to be ill-posed if you actually try to solve it backward in time. But for the Euler equation, there is no such arrow of time. The Euler equations are perfectly reversible. In fact, there's a coordinate transformation which transforms any evolution which is going for positive times into an evolution which is going to negative times. Okay, so now here comes what is our main interest in the talk. So the Kolmogorov theory of turbulence tells you, this is usually called K41 theory, and there is something which is called the zeroth law of K41 theory. And the zeroth law of K41 theory typically tells you if you have a typical turbulent solution of your equation, this dissipation, which if you were converging to a smooth solution of the Euler equation, so you're just imagining that you're solving Navier-Stokes equation, but with a small viscosity. And so even though there is this nu in front of the dissipation, which would suggest that this quantity is going to zero, as you actually solve it for a nu which goes down, if you're looking at the turbulent flow, what should happen is that this right-hand side stays bounded away from zero. Okay, so this one here stays bounded away from zero. Oh, of course, I forgot about this so far. So all of this is if the force were absent, but I have a force actually. So if I have a force, when I have a force, I have to add a few terms over here. So one term is going to be this one here. And of course, another term is going to be then appearing over here when I integrate in space. But the Kolmogorov theory, I mean, the usual formulation of the K41 theory is when F is equal to 0. So even though there is no action of an external force, you look at a typical solution of Navier-Stokes with, say, very small viscosity. If this is a turbulent solution, you're actually going to expect that the right-hand side is positive. So if this happens, of course, it cannot be that your Navier-Stokes solution is close to an Euler solution which is reasonable. So for an Euler solution which is reasonable, we just saw that you have conservation of energy. And so if you send nu to 0 and your sequence of solutions is converging to a smooth solution of Euler, the total kinetic energy is actually less and less dissipated. Okay, so let me make the following remark. For nu going down to 0, if the solutions of Navier-Stokes converge to a sufficiently smooth solution of Euler, then of course this term is actually converging to 0. Okay, so let me just put a small index over here just to say that I'm solving the Navier-Stokes equation with this nu, which is variable and which is going to 0. Then for every nu, I find a different solution. And so this thing actually is going to 0 as nu goes to 0. Okay, so the fact that this K41 theory postulates this thing is usually called anomalous dissipation. So why anomalous? Because if I were solving, say, the heat equation, so I don't put any advective term, and I'm just solving this equation with, say, a sequence of reasonable initial data. As I send nu to 0, I just converge to a solution of the free transport, and the solution of the free transport is conservative. There's not going to be any, there's not going to be a reasonable situation in which this thing actually stays bounded away from 0. Of course, what I could do, even if I were solving the linear Stokes equation, so this is maybe worth noticing. So if I introduce lots of oscillations in the initial data, of course, even if I'm solving the heat equation, the dissipation term will dissipate these oscillations very, very fast. So depending on what I do with this initial data, I actually could find myself into a trivial situation in which dissipates. I mean, for instance, if I insert as U0 say, cos of, say, a sufficiently oscillating function in terms of the viscosity nu, then just the viscosity term alone would be sufficient to actually dissipate all of the L2 energy. Okay, so therefore, if you really want to understand what this mechanism is, from the point of view of pure mathematics, you could actually pose the following question. So the Kolmogorov theory of turbulence is actually going to tell you that this anomalous dissipation should be a typical phenomenon. But as a pure mathematician who's studying partial differential equations, I would be already happy to just see one example in which this is happening. Okay, so this raises the following question. So say set f equals 0. So can you find a say even just sequence of solutions of Navier-Stokes with the following property? So if I really want to follow what Kolmogorov is doing, so I need a sequence of initial data with reasonable bounds. And okay, so what it seems like you want to ask, for instance, is that they're compact in L2, right? So if they're compact in L2, the initial data are converging strongly, and if you were like solving the linear equation, the heat equation, the solution of the heat equation would converge to the solution of the free transport. And if you have strong convergence in L2, there's not going to be any loss in the L2 energy because you introduced oscillation at the beginning. And anomalous dissipation. At some positive time t, say. Let's say a time t equal 1. Okay, and by anomalous dissipation at time t equal 1, I might simply maybe understand the fact that the lim-inf of this quantity, in which I'm just going to integrate what is the total dissipation over the time interval that I've looked at, stays away from 0. Okay. Okay, and as far as I know, the answer to this question is just completely open. And so you might imagine why. So typically in partial differential equations, what we are really able to handle, we're able to handle via, I mean, when we cannot somehow solve explicitly the equation, we are able to handle situations in which the solutions are conquered by some type of linearization mechanism or some type of regularization mechanism or some implicit fixed point argument and so on. And this typically requires that the solution is reasonably well behaved. Now, if you have a behavior like this, as I already told you, the solution cannot be well behaved. So the limit of these solutions cannot be a smooth solution of Euler. It has to be a sufficiently weak solution of Euler. And that makes any kind of rigorous PDE theory very challenging. Okay, so of course, here's one thing that you could anyway immediately remark, and this comes as a remark which was made by Larsson-Zager in 1949. So if such a sequence exists, then it's not converging to a smooth solution of Euler. You would expect that it typically converges to a solution of Euler which is dissipating itself kinetic energy. So to a solution of Euler which has low regularity. Okay, so expect such sequence to converge to an irregular solution of Euler which does not conserve the energy. And in fact, he put forward what went, at least in the mathematical literature, as Onsager's conjecture. And his conjecture was that this is typically possible for an irregular solution of Euler at a certain threshold. So if the Hölder regularity of the solution of Euler that you're looking at is 1/3. So the threshold regularity for this behavior is C1/3. And when you're looking at C1/3 functions, this means that your limiting velocity is satisfying a continuity assumption of the following type. Okay, and the threshold means at C1/3, it's not completely clear what happens, but say if you are a little bit below C1/3, then there should be dissipation of energy in your weak solution of the Euler equations. And so this has been the subject of, and Laszlo Zekaihidi was part of, and several other people. But so the conjecture was, so the conjecture is solved. So the conjecture is a theorem. And the positive part of the conjecture, so you actually need to be sufficiently irregular, was proved by Konstantin A. and Titi in the 19. So in the 90s. And the negative part was proved much more recently by EZ in 2017. And there is a whole story. And this whole story goes through what are called sort of convex integration methods to produce irregular solutions of the Euler equations. Well, of course, once you have done this, you want to go back to Kolmogorov and Onsager himself, actually, because he's deriving this conjecture as a limit of, solutions of Navier-Stokes, which you might regard as, I don't know, the true physical solutions. And what you would like to do is, like, I mean, naively, you would like to take some of these solutions which are irregular and which are produced by these methods, and see if you can approximate it with actual solutions of Navier-Stokes. And by solutions of Navier-Stokes, I mean solutions which are regular of Navier-Stokes. Because if you want to approximate them with irregular solutions of Navier-Stokes, but very irregular, you can actually use the same convex integration methods, but that's not really what you want to do. And this was done by Buckmaster and Bicol for other, like, very interesting theoretical reasons. But as I told you, you already face a very interesting question. So there is no way that an irregular solution of Euler, which dissipates the kinetic energy, is going to be easy to approximate via Navier-Stokes, because if you just focus on Euler, you don't see the arrow of time. So it's true that solution that you're looking at is actually dissipating the energy, but you can just make a coordinate transformation and reverse time, and then you find yourself a solution which is actually increasing the energy. And there is no way that a solution which increases the energy can be limit of a solutions of regular solutions of Navier-Stokes, because the regular solutions of Navier-Stokes has the energy which is always monotone in time going down. Okay, so this actually seems like a tall order, approximating solutions of irregular solutions of Euler with solutions of Navier-Stokes. So we know that for some of them, which are produced by these convex integration methods, is certainly impossible, because not only I have this problem of the arrow of time, but these convex integration methods even produce solutions for which the kinetic energy goes up and down, so does not have to have necessarily a sign. And on the other hand, it's also the case that if you are, say, for instance, starting with the two regular initial data, so it's true that you cannot put, like, say, too many oscillations in the initial data, because otherwise you get, like, trivial dissipation even through the linear equation. But if you're actually going to, like, say, put two strong bounds on the initial data, then we know from the theory that if you start with very smooth initial data, Euler is actually well posed for a small amount of time, at least, with a regular solution. And as long as there is a regular solution of Euler, the solutions of Navier-Stokes have to converge to it. This is like, a very general principle which can be proved in several ways. And of course, as I already remarked, as long as you're actually converging to a smooth solution of Euler, there's no way that you can have anomalous dissipation. Okay, so let me point this remark again. And this is like, a tenet of I mean, this is something that you can actually make rigorous with theorems, but the remark says that as long as there is a Lipschitz solution, if you're not accustomed to, like, jargon in the PD literature, let's say just C1 solution of Euler, any Lie solutions, and these are less regular than smooth solutions, so certainly it works for smooth solutions as well. So any Lie solutions of Navier-Stokes with vanishing viscosity has to converge to it. And so this obstructs essentially understanding anomalous dissipation if you're starting with an initial data, which is smooth, unless you understand some mechanism which is going to produce a blow up for Euler, which is still open. And well, there are actually now like, groundbreaking examples of solutions of Euler which blow up, which are sufficiently regular to be approximated by Navier-Stokes, but the nature of the blow up is very, very special. So they blow up at some point, and at that point, there's not going to be any anomalous dissipation. So it's even somehow worse than the typical situation in which you are hoping to prove, say, blow up for a PD, because in most of the situations that we know, the blow up of the PD is actually produced at a very small set, maybe at a point, maybe at a slightly larger set, and the singularity itself is well behaved. And you can actually produce many singular solutions of Euler. I mean, it does not have to be smooth. For instance, you have the shear flow of, two, layers of fluids which are sliding on top of each other. But all the explicit solutions which are singular, and so for which the singularities are tamed, they are actually not dissipative. Okay, so now let me just come to then the following question, which I posed with Elia Brouet in a recent paper, but which was posed by which was like already considered by other people in the literature too. And for instance, Peter Constantine is one person. And the question is the following. So remember that I gave you the forced Navier-Stokes equation. Sorry. So let me now put here new, and here Laplacian of u, and then let me put an f over here, and then let me put divergence of u equals 0, and the initial data. Okay, so I still have this force too. And I might ask myself the question, well, can I actually produce solutions of the forced Navier-Stokes equation in which the force is reasonable, but the solution displays anomalous dissipation? So what does it mean now? Well, of course, I can write down the balance law with the force also. And even with the forcing term, I can ask whether the dissipation term, which has nu in front, is going to 0 or not. Now, even if I have a force, I actually face a very similar situations to that of just having force equals 0 and reasonable initial data. Again, I have the same theorem as I had before. So if I give you a solutions of Navier-Stokes with a sequence of forces and the sequence of initial data which have, like, good bounds, in particular, if they are a little bit better than C1, I can actually produce, at least for short time, a limiting solution of Euler which has good bounds. And once I produce a limiting solutions of Euler which has good bounds, the solutions of Navier-Stokes have to converge to them. On the other hand, again, as it happens for the initial data, if I lower the regularity of the force, then I don't have any well-postness theorem for good solutions of Euler in the limit, and I can actually hope to produce an example of anomalous dissipation. Okay, and this is what we do in this paper that we posted this year on the web. So let me just modify my equation a little bit. So let me put a new over here. Okay, everywhere. And so let me now tell you the theorem that we are able to prove. Okay, so here's the theorem. So the theorem says, so for every epsilon bigger than 0, so I'm able to find an initial data which is fixed. So this one is nu independent. And sequences of solutions, and they are smooth solutions, of Navier-Stokes with nu going to 0 with the following properties. Okay, so first of all, as I told you, my initial data is fixed and it's even smooth. So there's no cheating on the initial data. It's actually very nice. Okay, then, of course, you might expect that given what I told you, there must be some degeneration in the sequence of forces going down. Okay, so F nu is uniformly bounded in C1 minus epsilon. Okay, so remember I told you that C1 is actually the threshold for well-postness in the limit. I'm just a little bit below the threshold, so I'm just Hölder regular, but by a tiny bit less than say what I would need to have well-postness at least locally in time for the limiting Euler equation. Okay, so and nu exhibit anomalous dissipation. That is the way I actually stated. So when I have the limit as nu goes to 0 of nu times the integral between 0 and 1, okay, this one stays positive. Okay, in fact, at the time, okay, maybe let me make the remark. So, so there are two important remarks over here. So the time definition, so the time interval of these solutions is 0, 1. And the dissipation happens at time 1. So these solutions are actually converging to they are converging to a solution of Euler, and this solution of Euler, of course, is also dissipating the kinetic energy, but we cannot quite actually relate the energy dissipated by the Navier-Stokes equation to the energy which is dissipated by this solution of Euler, which of course is going to be irregular, at least at time 1. So U does converge to a solution of Euler, and probably it converges better than what we're proving, but what we can prove is actually not exactly what we would expect. Okay, let me not be too precise on that. Okay, so before I tell you the idea which is behind this construction, which has its own interest and which has been influenced by other people in the other works in the literature, let me tell you where you would actually want to go from here. So this raises all sorts of questions. So I view this work as more like, raising interesting questions and an interesting direction of research. Because after all, the methods of proof are actually quite simple, like sufficiently simple at least. I mean, once I show you what is the idea. So this raises lots of questions. And of course, like one question that you might want to raise is like, okay, can I, of course, the idea would be like, it would be a super theorem if I could remove the force altogether. But then, as I told you, certainly we cannot prove it in that way without addressing, say, the blow-up problem for Euler, okay? So this is kind of maybe a very, very long shot. So can you remove F nu? Okay, maybe you cannot remove F nu. So let's say the best next question is, can you keep it at least fixed with the viscosity? So can you make F nu nu independent? Okay, if you make nu independent, you might probably have issues because it cannot be maybe too smooth. You actually have to resort to the solutions of Navier-Stokes that we know to exist, which are called Lie solutions. But these are still like typically very well-behaved solutions. So you might actually give up on this idea that you have completely smooth solutions because you don't know about the millennium problem for Navier-Stokes, but Lie solutions would be good enough. Okay. All of these questions can be asked in higher dimensions. Of course, they're not going to be as interesting in dimension 3, but from the pure PDE point of view, I don't see any difference. Like at the moment, I don't see a conceptual difference between having, say, dimension 4, 5, 6, 1000 and dimension 3. I can't do this stuff in dimension 3, and I can't do it in dimension higher than 3. And in some sense, dimension higher than 3 might just give you some easier geometry because you have maybe less constraints. But at the conceptual level, it's just the ability of understanding a certain mechanism which I lack in dimension 3 as I lack actually in higher dimension. And okay, so maybe this one is like, what bothers me most. So in this example, I told you that there is this anomalous dissipation over here. But somehow the anomalous dissipation all happens at time t exactly equal to 1. So our energy is like going to have essentially a sudden drop at t equal 1. So in our example, if I actually look at the limit as nu goes to 0 of this quantity at an earlier time, so I go a little bit before 1, then actually there's not any anomalous dissipation. So essentially, if you want, the dissipation is creating a Dirac mass in time at that time t equal 1. Everything is happening at that time at the same time. And it's not really what you would imagine should happen. So what you would imagine should happen, say, in the zeroth law of Kolmogorov, is that this dissipation happens like, gradually over the whole time, over the whole time interval. Okay. So can you give examples with, say, slower dissipation? Okay, and so now let me give you an idea on how you can prove this. And I mean, when we first posed ourselves the problem, at a certain point, we got the idea that so you will see from the idea there's a pretty simple, and you get the idea that you can construct something which has a reasonable forcing term and which is not creating dissipation. Which is creating dissipation. But what is actually remarkable in the end is that we are exactly able to reach this threshold, right? So this was an unexpected consequence of our work. So we were at the beginning certainly not expecting that our technique gives you, in a sense, the sharp regularity for this type of behavior. Let me also point out something which is really should be really obvious for people familiar with PDE. With this regularity at the level of the forcing term, if I take away the nonlinearity in Navier-Stokes, there's not going to be any anomalous dissipation. So if I just look at the heat equation, at the forced heat equation, and I give you the forced heat equation with dissipation which is going to 0, with forces which enjoy this uniform bound, and with an initial data which is smooth and fixed, the heat equation is just converging to the solution of the linear free transport with the limits of the force. And there's not going to be any dissipation whatsoever. So this is really, truly a nonlinear phenomenon, which when I will show it to you, you will see maybe why. Okay, so now let me spend the last, say, 15 minutes to give you a rough idea of the proof. I mean, not the details, because there are, of course, some technicalities and technical issues that you need to solve. But okay, so here is the idea. So first of all, we follow an idea which has been already used by other people in other contexts, not in this particular one. So let me see. So this is really something which has been used, for instance, by El Guindy and other people. But for our work, really, what was influential was a paper by Ji Yong and Yoneda. Okay, so here's the idea. So there are so-called 2.5 dimensional flows. Okay, in 2.5 dimensional flows are particular 3D flows of Euler. I'm just going to look at Euler, which satisfy the following structural condition. So you write down your velocity field u of x and t as 2 components. So v, which depends only on the first 2 variables, and the third component, say u3, which depends also only on the first 2 variables. Okay, so if you make these ansatz on your solution, well, V solves the 2D Euler. Okay, with whatever initial data. And the third component solves a free transport, which is transported by the solution of the 2D Euler part. So see, this one is, of course, exactly the solution of the first part. Okay, so let me just say this one is U3 initial. Okay, so now, of course, I am introducing a force. So I'm actually going to introduce a force only here. And the reason why I'm introducing a force only here is to produce a, so what I want to do essentially, I want to do the following. So I want to make U3 responsible for anomalous dissipation. And for this, I have at disposal some mechanisms which have actually been highly investigated in the literature in a completely different context, and in the context of transport equations. So in other words, one question that you can ask yourself is the following. So say that I give you a solution just of the transport equation, but I allow you to take a vector field V, which is not too regular. So can I actually make solutions of the, can I make, say, sufficiently irregular solutions of this transport equation under certain assumptions of V, which behave in a certain way? And then I want to actually find forcing F, which are going to produce the vector field V, which I like, which is producing the U3, which I like. Okay, so I want to make U3 responsible for anomalous dissipation through, say, a suitable choice of V. And then I want to choose F reasonable so to produce V, so to produce the desired V from the first equation, or which is 2D Euler, but in my case, it's going to be the forced 2D Euler. Okay, so that is like, say, step one. Okay, then I want to, this is going to be step two. Then I'm just producing a solution of Euler. So I want to add actually back viscosity. And I want to add back viscosity both on 2D Euler and on the free transport. And now it's where it actually comes tricky, right? Because you want to prove some sort of stability of the limiting solution, even though I put back viscosity. And as I told you, when I put back viscosity, the stability of the solution, of the Euler solution, is going to be very questionable because this Euler solution is not at all smooth. On the other hand, because the object which actually creates problems is U3, I am in a slightly better situation, because really for U3, what I'm actually looking at is a sequence of advection diffusion, of solutions of advection diffusion equations, in which the a vector field which is responsible for the advection is not that nicely behaved in the limit. But on the other hand, this equation now is essentially linear if I just think as V as something which you're going to give it to me. It's still problematic. So it still somehow gives you quite a bit of problems. So put back viscosity. and hope for some sort of stability, of VU3, but in fact, it's not that easy. And to really like, you know, so in fact, sort of say the naive stability that you would expect fails. Or fails. I mean, like I can't say really that it fails. The naive stability that you would want, we're actually not able to prove. But there is a very nice idea that we can use, which is sort of goes in this way. So if VU3 would be stable, then there would be anomalous dissipation because you're converging to this guy, which dissipates. On the other hand, if VU3 were not stable, then there would be anomalous dissipation also. Because when there is dissipation, strong enough dissipation, it actually helps you. I mean, when there is not strong enough dissipation, sorry, it actually would help you to prove stability. So there is a nice argument, which is essentially borrowed from another paper. And this paper is by Drivas, Elgindi, Iyer, and Jiong. Okay, so I'm not going to like, you know, enter into the details of step 1 and step 2. Sorry, of step 2 and step 3, but let me actually just focus on step 1. And give you a little bit of an idea of what is step 2. Okay, so how do we create dissipation, say, in solutions of the transport equation? Okay, so this is an idea which dates back to Depot, and which I have used in a completely different context in a paper by Kripa, and even more recently in a paper with Giri. And I used it actually to produce counterexamples in what is called the Perna-Lyons theory for transport equations. So something which in principle is totally different from this topic. And the idea goes this way. So let me take an initial data, which is some checkerboard. So I am in a 2D situation now, and so the initial data is going to be something like this. So there is a checkerboard, and the initial data U3 is going to be like, you know, 1 in these checker. I mean, in these I don't remember how you call them. Somehow on the white squares, and it's going to be like 1 on the black squares. So this is the initial data. Okay, it's not exactly Hölder as I promised you, right? I mean, it has actually jumps. Okay, so now assume you have actually a V. So as a V, you have a vector field which does the following. So take the dual checkerboard. So the dual checkerboard has like, you know, squares like that. So, and on the dual checkerboard, So this is going to be the dual checkerboard. Apply a vector field which is rotating the square by 90 degrees. So here there's going to be a vector field which you can explicitly write, which rotates each red square by 90 degrees. Okay, what happens when you apply this one? So say V, so say V rotates the red squares by 90 degrees in a time interval which is like 0, 1/2. Okay, so when I actually transport my initial data through this, what is going to happen is that U3 at time 1/2 looks exactly the same as before, but the checkerboard has been refined by 1/2, right? Because you have to imagine in here, this region in which the function was equal to 1 gets transported, and this region in which the function was equal to 0 gets transported to this region. Okay, so now you have your new checkerboard. And maybe you see what I actually want to do next, right? So next, I want to apply a rescaled version of V. In the time 1/2, 3/4, to actually refine again the checkerboard and make your solution 1, 0, 1, 0 on the checkerboard, which is even finer. Okay. So keep doing this. And when you keep doing this, the function, I mean, your solution keeps being 1 and 0 on finer and finer checkerboards. In the limit at time t equal 1 is actually converging to 0. With all the L2 norm, which disappears because there is weak convergence in L2 and not strong convergence in L2. Okay. So if you do this, when you're actually going to compute this quantity and take the limit for time t to 1, this thing actually is going to be equal to 1, but, or I don't know, to some constant, but U3 actually at time 1 is equal to 0. Okay, and now what do I want to do? Well, now I want to do something very, very silly. So now take V. So take V, feed it to Euler, and produce a force. Okay, so when I take V, essentially I just have dtV plus V dot grad V. Okay, I have to make, say, the Leray projector of this so that I take away the gradient. And this is my force. Well, if I do this, I actually get, of course, a force which is quite irregular, right? So because my vector field V is jumping. But anyway, at the heuristic level, so at the heuristic level, F is not big. The reason why it's not big is because when you're actually making smaller and smaller your checkerboard, the size of the vector field V, so the size of V, is proportional to the side of the checkerboard. So now what I argue So what it really goes into the proof for step 2 is, well, I don't need to be, I mean, okay, so I want actually, so this vector field V in the jargon of transport equations and PDEs is said to be mixing. Now, I don't really need to make V having, you know, this huge jump. I don't really need to have this checkerboard situation completely equal to 1, 0, 1, 0. An approximation of this actually does work. So I can still smooth V a little bit, make it actually C infinity, and still get a picture which is approximately like the one of the checkerboard. And okay, so here it comes a like, you know, important work by, so say what we want to do is to regularize V. And for this, we use a work on mixing, which has been very influential by Alberti, Trippa, and Mazzucato. And so this, in this realization of V, of course, now you have, I mean, the sort of hard details are actually hidden. So now you have to go make this realization and compute Hölder norms. And it happens that for some miraculous reason, which, I mean, I still don't understand beyond simply giving you the actual computation, you get all the way up to the threshold C1. Okay, and I already explained to you that step 3 is through this beautiful idea by Drivas, Elgindi, Iyer, and Jiang. And so here, just let me stop with my talk. Thank you for your attention.
Well, thanks a lot, Camillo, for this wonderful talk. I now leave the floor to the audience for questions or comments. So actually, maybe I have actually a few. So the F then is rather explicit. I mean, the vector, the forcing you introduce in the equation is you constructed it like that. So it's an explicit.
Yes. Yes, okay. It's rather explicit, and it's even, I mean, it's even more explicit, meaning that when I actually put Navier-Stokes, I also like, okay, I try to keep, I mean, I regularize V even more because I wanted C infinity, but then I feed it to Navier-Stokes so to get the force. And then I try to show that, you know, the advection diffusion equation still behaves reasonably. Mm-hmm. So yes, F is awfully explicit.
Yeah. And so what you said is that so if the, I mean, this is a naive question probably. So if the regularity is above 1, then it's known that everything is well behaved.
Okay, so if the regularity, so let me be a little bit more explicit over here. So, I mean, if the regularity is above 1, there is a smooth solution. I mean, there is a reasonable solution of Euler that the Navier-Stokes equations, solutions of the Navier-Stokes equations have to converge to. Mm-hmm. For a fixed time, though, for a fixed time. So for a fixed time, say 0t. So this just means that I told you that this is happening at time t equal 1. But time t equal 1 really doesn't play a role. I mean, I can make it happen even at earlier times if I want. I just have to tweak the parameters of the construction. Now, if I go above C1, this cannot happen after a certain time has elapsed because there will be a reasonable solution of Euler in the limit. So the only way this could happen is because, you know, the reasonable solution of Euler blows up. Mm-hmm. And after it blows up, it starts being like, you know, even nastier and it dissipates because the blow-ups that we know, like now from very recent works, for instance, by Elgindi in the C1 alpha category, they're just very reasonably behaved blow-ups. Mm-hmm, mm-hmm. So in that sense, that cannot happen above C1. It cannot happen sort of this way, but of course, you know, you might very well be able to, like, say, solve the blow-up problem for Euler and, you know, create after that a nasty solution of Euler, which is even dissipating the kinetic energy, and then there is no obstruction to have the anomalous dissipation.
I see. Yeah.
Can I ask a question? Huh? Oh.
Yeah.
Oh, yes.
Yes.
Okay, so you said that to have new independent F is a difficult problem, but so in this construction, what do you know about the new dependence of your force?
Yes. Okay. So, so at the intuitive level, this construction should actually give you something which is new independent.
Yeah. That's what I naively thought.
But it becomes a very subtle question on whether your solution of Navier-Stokes, okay, because you know, this kind of, I can put that F and I can put that U, right? So that is the Euler equation. And then I can put that particular force that I found into the Navier-Stokes equation. And then I have to show you that there is enough stability, so that the solution of the Navier-Stokes equation is converging to this solution of Euler, and in a sufficiently nicely behaved manner, right? Because the third equation is not exactly that nicely stable. So it's at that point that I have actually a lot of PDE problems. And the reason why I have a lot of PDE problems is essentially the following. If you don't tell me anything about, you know, the limiting solution of Euler, you just tell me very little and very little regularity, how do I compare nearby solution of Navier-Stokes? Essentially through some energy method, which is going to give me some Grunwald inequality. And that is like absolutely awful. So it's way too weak to actually show that there is enough stability to show that this phenomenon persists. I mean, it's really, so if you are like, you know, a theoretical PDE guy like me, it's really like what I told you at the beginning. So when are you able to prove, without knowing a lot about the solution, when are you able to prove enough stability to say that you're converging nicely? When the final guy is smooth, then you can do all sorts of things. You can linearize, you can get all nice estimates. If the final guy is not smooth, you essentially have very few methods to prove stability, and they are very weak. They give you only very qualitative and non-quantitative information. So even at this level, in this step 3 that I told you, we already face that problem. And there is this nice dichotomy, which we learned from this paper by Drivas, Elgindi, Iyer, and Jiang, which essentially like bypasses the problem, the hard PDE problem of really proving that the advection diffusion equation is as stable as you would expect. So for instance, like our model solution of Euler dissipates all of the kinetic energy, right? So like, you know, it has the kinetic energy and it converges weakly, and then it's equal to 0. So the L2 drops from 1 to 0. In our proof, what is the dissipation? In our proof that this limit over here is positive, we don't prove that this limit is 1. So we don't prove that it dissipates as much as you would expect from Euler. I mean, we prove that it is positive. I don't know, 1/2, 1/4, a small constant. So in that sense, we are not proving that much stability of the final solution, of the final Euler solution.
Yeah, thank you.
Thank you. Other questions or comments?
Could you tell us what was the motivation of Kolmogorov in 1941 to make his conjectures, and then the motivation of Onzaga? I mean, probably some heuristic arguments. I mean, it was a long time ago.
Yes. So of course, so for them, they are trying to make a statistical theory of turbulent fluids. I mean, for Kolmogorov, this zeroth law is really zeroth law. I mean, he's not even like, you know, spending that much. It's not even spending that much, time on it, or like, you know, simply from the data, you see that this happens. And you know, this is like essentially the starting point for deriving other considerations of statistical nature. it's somehow similarly for Onsager. So for Onsager, the interest was more like, this threshold exponent. This is 1/3. So of course, in all of these turbulent, literature, what your picture is something of the following type. So you can take, say, this is what Onsager does. So you can take the periodic solution of Euler, and you can introduce Fourier coefficients, and then you can look at this as an infinite dimensional system of ODEs on the Fourier coefficients. And you're making some statistical considerations, and under some statistical consideration, there is an energy flux from, say, lower modes to higher modes. And you can derive somehow power law for the spectrum by making, say, some adimensionality assumptions on certain constants and things like that, and then you derive certain interesting scaling laws that you're expecting for the dissipation, for the energy spectrum, and so on. But this assumption that there is anomalous dissipation is always the starting point. So honestly, at the level of, why the dynamical system, say, even when you write it as an infinite dimensional ODE, why the dynamical system should do that, to me, it's a sort of a mystery. Of course, you can like, write down models which look similar to what Navier-Stokes is, and this has been done quite a lot in the literature. And depending on how you work out these models, you can see this transfer of energy from, like, lower modes to higher modes, which ends up into this anomalous dissipation. So essentially, there's lots of transfer of energy which is given by the nonlinearity, and then at a certain point, when you get to sufficiently high modes, the viscosity kills it completely.
Thank you.
Why 1/3?
Why 1/3? So that comes out of consideration on the energy spectrum. I mean, there is, like, what is called Kolmogorov's fifth third law. So essentially, like if you okay, so if you write down what you're expecting to be the energy spectrum for this equation, you can look at how much how much L2 size there is in a certain Fourier shell. So this is predicted by this energy spectrum, and the way the power law is predicted for the energy spectrum is to make a certain constant independent of the units of measurements. That is what typically done in the theory of turbulence. Okay, now at that point, you can simply see, from this energy spectrum, if you have, say, a typically like a Fourier expansion of your solution, and you know what is the L2 size of the Paley-Littlewood shell, then you see that the critical regularity for having that energy spectrum is having essentially 1/3 of the regularity, right? Something like that.
Thank you.
Other questions or comments? It does not seem to be the case. So let's thank a lot again, Camillo, for this very beautiful talk.
Thanks to you.